Hello everyone, I'm Michael, and my project was acceleration-constrained quadrotor trajectory optimization in dense obstacle fields using graphs of convex sets. The motivation for this project comes from the assessment that in future military conflicts, the number of piloted medical evacuation aircraft will be insufficient, giving rise to a need for autonomous air ambulances that may require aggressive maneuvering in urban environments. The methodology begins by creating a dense obstacle environment, followed by creating convex safe regions that starts by creating a visibility graph, followed by cleat covers, which are circumscribed in ellipsoids and are inflated with polytopes. Next, we use GCS as described in class to find the optimal path between these convex regions. We then retime this path with TOPRA with acceleration and velocity limits. Then we use differential flatness to recover the full quadrotor state from the flat output states. Then we finally use a finite horizon LQR for trajectory stabilization. The simulation environment consisted of 50 randomly generated obstacles. We then bound each obstacle with a 0.2 meter box. We then create 20 safe convex regions covering 71% of the obstacle-free space using cleat covers and iris, which took 27 minutes. Note that uncovered regions cannot have GCS trajectories be in, from, or traverse through them, as shown here. Next, we run GCS with a 5 meter per second velocity limit, with time and path cost, which solved in 9 seconds. The trajectory is seen on the right. Then we retime with TOPRA with the same velocity limit, but adding a 3 meters per second squared acceleration limit. Then we recover the full state and control using quadrotor differential flatness. The experiments run were GCS only, GCS plus TOPRA, and then a bonus 100 obstacle environment. The acceleration results also show tight tracking, but demonstrate some discontinuities and accelerations upwards of 20 meters per second squared. That's over 2 Gs, which could also be unsafe. Now that we've shown that GCS-only trajectories may not be suitable for autonomous air ambulances, let's add TOPRA with a 3 meters per second acceleration constraint on top of it to see if it's less aggressive. It still tightly follows the path, and it looks less aggressive. It makes less angular rotations and movements. Finally, the GCS plus TOPRA acceleration shows that the desired acceleration of 3 meters per second squared is met. However, the actual acceleration exceeds it, upwards of 8 to 10 meters per second squared. This requires better online control, such as linear MPC. There are many avenues for future work. First, I'd like to investigate why the GCS-only trajectory violated the velocity limit. Next, I'd like to implement nonlinear GCS to ensure jerk and acceleration continuity. I would also like to modify TOPRA to include angular velocity and acceleration constraints. The references for this paper are shown here. Now here is the bonus 100 obstacle environment. Thank you everyone for watching my presentation.